just get started, and we'll wait for a few others to trickle in. So today we're going to talk about K-nearest neighbors. However, before we do that, I want to very briefly talk about your project for the semester, because the first part of your project is going to be due fairly soon, February 11th. So your project this semester is to build a machine learning model. That's it. There are some parameters. There's some restrictions as far as the data that you can use and what deliverables I want to see at the end. So first, teams. You can work in teams of no more than 3 students to complete your project. If you prefer to work individually, that is completely fine with you. Completely fine with me. Work however you work best. The data set that you select for your project, I do want this to come from an established repository. So I'm going to ask you to pull your data sets from the Kaggle dataset library. If you're not familiar with Kaggle, we can go ahead and head there now so you can see what this looks like. So Kaggle is a website full of machine learning competitions, companies, academics, all kinds of people post data sets here and essentially give prizes or bounties to people who come up with the best predictions. So right now, as you can see, there are currently 11 active competitions. You may choose your data from any one of these or from any of the previous about 360 competitions that have been done and completed on Kaggle. So you have a lot of data sets to choose from. The only restriction that I would maybe recommend is avoiding problems involving image classification. Right now, I'm not sure that we'll get to image classification. If we do, it'll be late enough in the semester that it'll be difficult to fully complete your project analysis on time. So avoid that if you can. Otherwise, the choice is up to you. For those of you who like a little bit more structure, I've gone through and curated a list of a couple different Kaggle competition data sets that I think are interesting. So there's one that was posted by a website called Pet Finder. They wanted to come up with a prediction for whether or not pets listed on their app would be adopted. The PBS Kids Measure Up app, this is an app that children can use to play games, do learning activities. They've released data from that. If you like sports, the NFL Big Data Bowl is a good one to look at if you're looking for a job in machine learning. You might be interested in the Kaggle Machine Learning and Data Science Survey. We've got revenue from the Google Store, Zillow's home value prediction data, and then we have an energy predictor. So how much energy will a building consume? Again, any data set that is posted on Kaggle is totally fair game. These are just ones that I think might be more suitable than others for the project. Outside resources, you can supplement or adjust your data set in any way that you wish as long as it's justifiable. So you can add data from other sources to augment your data set. You can manipulate the variables in your data set. Any changes that you make, you should be able to justify to a client or a supervisor. But those changes are completely up to you. You may use these publicly available Kaggle notebooks as a reference only. So every one of these Kaggle competitions, let's go, for example, to the Data Science Bowl. This is the PBS Kids app. One of the great things about Kaggle is that users post their work. So you can see what some other users have done, what some other approaches to analyzing this data set are. In fact, I'll ask you to review these other approaches later in the semester. So you are welcome to use these as a guide to get started, but they should not be the basis for your analysis. Any analysis that you produce or present should be your own. So then, what I'd like to see, there's going to be a couple checkpoints for this by Tuesday, February 11th, so 2 weeks from now. What I'd like to see you do is select your team members and your data set. So I'd like to know who you're working with, if you're working with a partner, and what data set you'd like to choose. For your data set, you should come up with some research questions that you could use the data to answer, and then you should categorize or frame those questions. So is it a supervised or unsupervised task? Is it a classification or a regression task? Then after spring break, I'll ask each group for a status report and a work plan. So how do you plan to finish your project during the semester? Between Easter break and dead week, you can plan on presenting. The number of days we'll take to present depend on how many groups there are. Any questions? Yeah.
Is there any set size for these databases that you would say we should be working with?
No, so there's no set size as far as number of observations, number of parameters. Typically the data sets posted to Kaggle are not small. If you choose to reduce the data set for any reason, that is okay. It should be justifiable. So for example, maybe you would focus on states in the Midwest, something like that. Jake?
So at this point in the semester, presumably we've not learned about all of the machine learning techniques that we're going to learn about in this class.
Correct.
So do you have any recommendations about like what we should look for in a data set? Like, oh, you should try to avoid picking data sets with too many categoricals or with too many, missing values or like things like that.
Not yet. So the question was, do I have any guidance for things that you should avoid when picking data sets? Other than image classifiers, no. I think we'll get through most of these sort of topics in a reasonable amount of time. The other thing that I would maybe steer away from, unless you have some experience doing it, is text analysis and making predictions with that. If you are experienced working with text analysis and you would like to do that, awesome. Otherwise, though, categorical predictors, categorical inputs, outputs, numerical, what have you, supervised, unsupervised, we will cover it all in sufficient time. Other questions about the project? Okay. So then again, February 11th, I would like to know who you're going to be working with, what your data set is, and what your research questions are going to be. This is not something that requires like a massive write-up. I've just given you a text box to enter this into. And only one person per group needs to do it. Okay, so that is the project. So let's go ahead and jump into K-nearest neighbors. If you remember K-nearest neighbors from Introduction to Data Science, this is a fairly intuitive, fairly simplistic technique. So we'll talk about how K-nearest neighbors works, and then we'll spend a little bit more time today on optimizing some of these models and setting up a search grid for coming up with parameters to these models. So let's introduce K-nearest neighbors. And one of the wonderful things about K-nearest neighbors is that it's about as non-parametric of an approach as you can get. What I mean by that is that you don't have to make any assumptions about the distribution of any of the variables in order to use K-nearest neighbors. Essentially what you're doing is just looking for similar observations. You're looking for observations in the data set that are somewhat close to the observation that you want to predict for. You're basing your prediction completely off of those nearby points or those neighbors. So essentially, for some positive integer k, what we do in k-nearest neighbors is figure out what are the k-nearest neighbors, what are the k closest points, either by a basic distance calculation or some other similarity measure. And then we just classify that new observation to the category that the nearest neighbors most agree with. So we look for how many of the nearest neighbors fall into each class. We choose the class with the most nearby points. Now in 2 dimensions, k-nearest neighbors is really easy to visualize and think about. Let's go through a formal statement of what this is actually doing first. So formally, notationally, we're going to let XO be our new classification point. We'll let X, or capital K sub 0, represent the set of the K points that are closest to that X0. So then what we want to do is come up with an estimate of a conditional probability, just like we did using a Bayes classifier. So we'll come up with the probability that our output Y is in class J, given that the inputs are at a particular location, just by counting up how many of the nearby neighbors fall into each class. So whichever one of these has the largest probability, that's how we'll make the classification. If we're in the situation where there is a tie, we'll choose at random between the ties.
So I just want to make sure I'm not totally off on this. Is this kind of like the same idea as neural networking? Like, with the probability of nodes?
Not quite. It's not quite the same idea as neural networks, but the output is the same in that we're predicting a probability of falling into some class. Neural nets add several more layers of complexity to this. All right, so there are practical questions that when we're implementing k-nearest neighbors we need to answer. The first is the distance. If we need to figure out what k points are closest, how are we going to come up with that measure of closeness? What will I use to define the distance? And we've got several different choices for defining this distance. We also need to choose how many neighbors to pull. So what k are we going to use? These choices aren't as easy as they seem, and our predictions are going to be choice dependent. Depending on the number of nearby neighbors we select, we may have a different prediction. Depending on how we measure that distance, we may have a different prediction. So we'll stick with the iris data set just to illustrate how k-nearest neighbors works. So this is the iris data set again. We have each of our 3 species of irises. We've got Setosa here in the coral, versicolor in the green, virginica in the blue. I'm going to select a new data point. My new data point is right here in yellow. I'm going to select sepal length 5.5, sepal width 3.7. Intuitively, just looking at where that point falls, it's right in the middle of the setosas. So it makes sense, or it might make sense, that we'll predict that to be a setosa. So what I'll do is draw a circle that encompasses the 5 nearest neighbors. So we have 1, 2, 3, 4, 5. All 5 of those are setosa. So the probability that a nearby iris is a setosa is 1. Probability of the other classes is 0. So we'll define, or we'll categorize that to be setosa. If we increase the width of that circle, so if we draw a larger neighborhood, we'll start to draw more observations in. It could affect our decision. If we're looking at predicting points that are right in the middle of the class, this isn't too difficult of a problem. Let's say we've got this new point, though, in yellow. X is 6, or sorry, sepal length is 6, sepal width is 3. Looking at our nearby neighborhood, we have 4 points that are right inside the circle. We have 3 more that are right on the boundary. So let's look at what happens when we define those 2 neighborhoods. So looking at the neighborhood where k equals 4, so everything inside the circle, the probability that a nearby neighbor is a setosa at that point is 0. Probability that y is versicolor at the nearby point, using the 4 nearest neighbors, 2 of them are versicolor in green out of those 4, so we have 2/4 or 1/2 probability. Probability of virginica at that nearby point is 2 out of 4. Our probabilities are the same, so we'd have a tie. For this one, we would classify at random. We would pick one of those 2 by chance. Yeah?
Is there any modified function that you know of where you can pass it like a parameter to tell it not to pick at random, to like maybe calculate the mean distance and pick the one that is closest distance-wise?
So there are certainly implementations that will do that. So instead of picking at random, we might pick based on the one that's closest. The most common implementation of k nearest neighbors in R, which is just simply k and n, if there are ties like this, it will pick at random. Say that the 4th and the 5th farthest observation are the same distance away. If we want to choose k to be 4, we'll actually take both of those at a tied distance. So we'll bring in that 5th. One thing that you'll see a lot of people do in practice is purposefully choose an odd number for k, or a number for k that is not divisible by the number of classes. That forces us not to have a tie. So that's a simple solution to that problem. Now say we take everything that's on the boundary of that circle as well. So instead of having k equals 4, we'll go to k equals 7. There's no setosas around the boundary, so we're adding these 3 points. Our probability of versicolor is 5 out of 7, virginica 2 out of 7. So we'll classify that point to be a versicolor, or green. Here I'm defining my distance just using straight line Euclidean distance. So I'm only drawing a circle around the points. Once we get to more than 2 dimensions, it gets a little trickier. Questions so far? If we increase this even farther, our prediction may or may not change. So here we have a new circle. What I'd like you to do is take a few minutes, either on your own or with someone sitting next to you, to walk through this exercise, identify k, and decide what class we choose at this distance.
There's a lot of counting. It's definitely green.
It's
These are 8 or 13
versus
oh, yeah.
513.
So,
Yeah, it's 13. So.
because like I don't know whether it counts the ones on the edges of the circle, but I would guess no. Because that's mostly inside.
Yeah, well, if you count those, there's like 3 of them. There's 2 at about
It didn't change
7
anything.
o'clock or something.
But it does change it over
Knowing that
But
there's
yeah, it's
3 on
definitely
the circle, so like 13.
Yeah.
Versicolor, so probably k is 13, and then what class would they choose? 5 out of 13. So 8 and 13, so probably the first one, right? Because 8 and 13 are. Right.
So what's our k for that new circle?
13.
13, yeah, 13, depending on what you do with those edge cases. What's our probability for versicolor using that k?
8 is 13.
Okay, 8 out of 13. So virginica, 5 out of 13. So our prediction has not changed. Now, picture for a minute, instead of predicting here, let's picture predicting over here. So say at sepal length equal 8, sepal width equal 4. Where are the 13 nearest neighbors for that point? They're far away. So if we're predicting here, our 13 nearest neighbors encompass a lot more space or a lot more area than the 13 nearest neighbors do here. So when we have more distance between the points, or when we're trying to predict in regions where we don't have a lot of data, we sometimes have to look at pretty far distances to get those near neighbors. Yeah.
But the algorithm doesn't draw like uniformly sized circles, right? It just takes the nearest neighbors at each individual point.
Correct. Yes. So we are not using uniform sized circles around each prediction point. If we did that, we would run into areas where there were no nearby neighbors. So what we are setting uniform is the number of nearby points to select, not the distance. Yeah.
For changes you would make using weighted distances, will that reduce the confidence based on the distance as well?
So for predictions that you would use using which types of weighted distances?
So like in this example, you would add a lot of credence to those two blue points in comparison to like a further away green one.
Mm-hmm.
If we put one up in that gray area where there isn't a lot, if we don't weight the distances, we just say blue. But if we weight the distances, would it be like we think it's blue, but we think it's blue with way less confidence than something
Got
drawn
it.
in the middle of the blue ones?
Okay, so the question is, say that we want to be really confident about a classification. Do we give more weight to these nearby points than to the far away points? The answer in base k-nearest neighbors, no. There are flavors and modifications where you will give more weight to these distances. You certainly can do that, but in most implementations, we don't. We treat all nearby neighbors the same.
And I'm guessing it probably steps pairwise through each individual combination and then ranks them and then picks the top K whatever and then says this is how I'm going to classify. So like now you're not drawing a circle, but you're actually calculating distances of every single other point with respect to that one point that you're at.
Absolutely. So we are calculating, in order to implement this, pairwise distances, so the distance between each point and every other point, sorting or finding the closest K, and then making our prediction based on those. So this can be a fairly heavy algorithm, depending on how you code it. Other questions? So let's talk about the distance measures that we have to use. The most simplest distance measure that we could implement is Euclidean distance, or just take the straight line distance between any two of the points in p-dimensional space. So for 2 points in p dimensions, we'll let bolded xi be the vector of all of the x values for observation I, xj be the vector of points for all of the xj's, and then we'll calculate our distance by taking the sum, and apologies, this last one should be a minus, not a plus. So we'll take the difference of x variable 1, points I and j, square it, variable 2, points I and j, square it, variable k, points I and j, square it. Again, that should be a minus, not a plus at the end. So we'll just calculate our right triangle or Euclidean distance. This is the default in most implementations of k-nearest neighbors. If you're working in caret, we'll set method equal k-n-n to set this up. Out of curiosity, show of hands, how many of you have taken Math 350? That's Intro to Linear Algebra. How many of you feel like you remember it? Okay. We'll probably have to take a break and do a matrix day at some point. So look forward to that. Here's another distance measure that we could use. This is Minkowski distance. So Minkowski distance is a more generalized distance measure. There is an additional parameter for Minkowski distance, that is p. P here is perhaps a bad choice because it's not the same as RP in the input. This is allowed to choose, or allowed to change, excuse me. So our Minkowski distance is going to be calculated by taking the sum of the absolute value of 2 points raised to the p power. Once we've taken that sum, we'll raise the whole thing to the 1 over p power. So Minkowski distance and Euclidean distance. Euclidean distance is Minkowski with p equals 2. So they are definitely related, or they are exactly related in that way. This Minkowski distance is a bit more generalized because we can set that p parameter to be any positive value. So for example, if we have 2 points, say if we have 2 points or 2 variables, x1, x2. The set of all points at the same Minkowski distance, the same Euclidean distance, forms a circle. It's not true for Minkowski distance. The set of all points at the same Minkowski distance, say, for example, p equals 1, is a diamond, not a circle. So we're defining that shape or that geometry of the nearby points a little bit differently when we use Minkowski p not equal to 2. There may be some advantages to doing that computationally. We may get better predictions. We may get simpler calculations as well. Or we may get something that's a bit more tractable given what the data looks like. Depends on the situation. Jake.
Do you get to rotate the diamond?
Sorry?
Do you get to rotate the diamond? Like, do you get to choose how it's oriented? Minkowski?
No.
It's just always like.
Yep, so the Minkowski diamond is always diagonal like that. Other questions?
Does it get weird after you pass 3, 4, 5 as the p parameter? Or?
It can get weird. Yeah, maybe make a note of that. Let's play around with this if we have some time.
It's a little Rick and Morty.
It gets all, you can do fractions, that's weird.
Yeah, that's fun. You get some cool, like,
Just slowly
flowery
turn square.
shapes. If we have time, we'll play with it. Or maybe in a lab next week we'll play with it. Okay, so let's introduce a new example. So this data set comes from a library in R called the ML Bench library. ML Bench stands for Machine Learning Bench, or benchmarks. These are data sets that have been used in a lot of machine learning papers as benchmarks to test how well an algorithm works. So they're well-studied data sets. This data set comes from a study done at the University of Wisconsin-Madison. Researchers wanted to classify samples as either benign or malignant tumors. So they had data on the cell thickness, cell size, cell shape, marginal adhesion, epithelial size, bare nuclei, and so on. All of these explanatory variables are normalized to be integers on a scale from 1 to 10. So essentially we're looking at percentile, or quartiles, or quantiles of these. About 1/3 of the tumors that were sampled were malignant, about 2/3 were benign. So we're going to use all of our variables here with the exception of patient ID. We'd like to remove that. Hopefully that is for obvious reasons. This patient ID certainly isn't something that we can build a model on and make predictions for a new patient. So we'll need to remove that before we build our model. We'll do that by creating our training index. Here I'm going to use create data partition to generate a balanced sample. I'm going to use a 75-25 split. To remove ID, I've removed it at the model fitting level. So I've removed it from my model formula, and I get an error. I get an error here. That's a little bit mysterious. Let's take a look at this data set and see if we can diagnose the error. So I'm going to switch over to R. We'll kick this over to the monitor that's being recorded. Let's scroll up to where we load the data. Any ideas what could perhaps be causing that error or how we could find out?
I'm gonna assume it's a data type error just because I've seen the error.
Okay, so it might be a data type error. What other errors could we maybe run into when we're fitting a model?
Is it possible that some of those columns have blanks in them that make the number of observations not match up?
Yeah, it could be a missing data type of error as well. A simple way to check would be to use a function like summary. This automatically calculates summary statistics for different variables. We do have, it looks like, some NAs. So we have an NA for the number of bare nuclei. We've got 16 observations missing here. We haven't talked about how to deal with missing data yet. We will in just a little bit. For now, though, we'll just remove those missing observations and see if that is helpful. And it will be. So I'm removing these missing observations in the following way. I'm using a function called complete.cases to check whether all of the rows in the breast cancer data set are complete. If all of the rows are filled in, meaning there's no missing values, complete cases will return true. If there are rows with missing data, complete cases returns false. So this notation means that I'll keep all of those rows in the data set for which breast cancer is complete, and then I'll keep all of the columns as well. So I'm going to save this new data set as breast cancer 2. It's got 683 observations. So we've removed those 16 with missing values. There is also a problem with the variable types in this data set as well. So variables 2 through 10, those explanatory variables, are coded as ordinal factors. So they're coded as 1, 2, 3, 4, 5 in order, but they're not representing numerical variables. R thinks that they're factors. To make our life a little easier, we're going to reclassify them as numerical. I'm just going to do this in a for loop. So for columns 2 through 10, I'm going to rewrite that column with the same data just stored as numeric. So that's what's happening here. Now that we've fixed up our data a little bit or cleaned it up, we'll recreate our training, our test data, exact same way as before. And then finally, we'll fit the model. I've went ahead and removed the ID column at this step by writing -1 in the column space in the brackets. That means remove the first column. So I no longer have to keep track of that ID column when I fit the model as well. So let's just see what we get when we try to predict class based on everything else.
So you transform these factors into a number, and I think that's because this is like an index from like 1 to 10. Are
Yes.
there cases where you wouldn't want to do that?
Yep, there are absolutely cases where you wouldn't want to do that. However, with k nearest neighbors, we want to calculate that distance, so we do need it in numerical form. Yep. If there was some reason why those 1s, 2, 3s, 4, 5, 6, 7, 8, 9, 10, if they did truly represent categories, then we would want to keep them that way. We might use a different method. Jake.
Does k-nearest neighbors work better or worse for continuous or discrete data, or like especially for discrete data like this, where your values for your input variables are bounded to a relatively small range?
The answer is it depends. And it depends more on some of the other characteristics of the data. So k-nearest neighbors, for example, doesn't work very well when n is small. It's because you don't have a lot of data to build those neighborhoods with. The more data points you have, the better it works, and the better separation you have between the classes, the better it works. That's really more of the indicator rather than continuous versus discrete. Other questions? So here is our model. We have 9 input variables, 2 classes that we're predicting, benign versus malignant. We've got 3 different values of k that we're selecting. We're fitting this model with k equals 5, so choosing the 5 closest points, choosing the 7 closest points, and choosing the 9 closest points. Accuracy is pretty similar between those, however accuracy is slightly higher when we choose the 7 nearest neighbors. So our final fit is going to use the 7 nearest neighbors. Why 5, 7, and 9? Josh?
To avoid ties.
We're avoiding ties, yep, by taking odd numbers of neighbors. Still, if we're in a situation where we have hundreds or thousands of points, maybe if we take more nearby neighbors, we might get better predictions. So this 5, 7, and 9 is certainly an arbitrary choice. By default, Caret will choose 3 values of the parameters to test unless you tell it otherwise. You can tell it otherwise. Looking at a plot of these results, so here's the accuracy with 5 neighbors, here's the accuracy with 7 neighbors, here's the accuracy with 9 neighbors. Again, 7 looks pretty darn good, but the scale goes from 0.957 to 0.959. So no matter which number of neighbors we're choosing, we're getting some pretty good classification on the training data.
Does Caret have a specific way that it chooses? So it chooses 3, but does it have some sort of algorithm, like rules-based way of choosing which 3?
Absolutely. So it'll choose which 3 algorithmically. How it chooses which 3 tuning parameters depends on the method. So for each one of these methods underneath, there is an algorithm that it's using to decide which tuning parameters to test. Other questions? Okay, so let's say that we want to have a little bit more control. We want to choose our own K to try. So I'm going to try lots of different Ks. I'm going to create a data frame or a data set in R called K. And that's going to take integers from 5 to 50. So I'm going to try 46 different values of k, just to get an idea of what happens when we switch this k up. There's a new argument in train called tune grid. Most of the models that we implement do have this argument somewhere. Tune grid represents the parameters that you have the option or the ability to manually set yourself. The more values that are in your tuning grid, the longer this will take to run. K nearest neighbors still doesn't take too long. Here's the accuracy for k equal 5 up to k equals 50. What tends to happen is that you see a lot of bounces relatively in accuracy where k is small. As k gets bigger and bigger and bigger, the accuracy will start to drop.
Is that a product more of our number of observations than it is really the model? Because if you are excluding the whole group of Setosas, or whichever one was off in its own corner, like, does that tell us more about our data set than it does about model accuracy?
So this is actually a question that I want you guys to take a few minutes to think about. So here's the question. We're classifying based on this probability, right? We're classifying based on the probability that y is in group k with the nearby neighborhood. So the question is, what happens to this as k approaches n? Take a few minutes to talk it over.
So that is.
I mean, once you're pulling all the points, or
If
even
the y
a
equals
good
y,
chunk of the points,
y equals k.
effectively what you're doing is which
Literally
is
just
the
X
most
equals
common
X.
class.
So as it gets bigger, you end up with that means one of those two things.
Category has the
I'm
most
not sure.
points.
There's-
So k indicates.
But if that's go back to
So it's kind of that conditional prognosis. I know this because this is all I do. So that given that y equals k parking.
But I also at the same time
Yes,
think,
smaller
actual
and
size
smaller.
of that
20 minutes.
is
Yeah,
like
I would love to see
literally
how
all the
I
much
choose.
Yeah.
What does that actually mean for us? It's not like we're not like
This one,
22
you have to, think of it, that
Times
was
probability. So that conditional probability is getting.
But you also have location.
So what happens to this probability as K approaches N? I heard it a lot as I was walking around.
Becomes a frequency distribution.
Absolutely. This just becomes the class frequencies in your training data. So what are you going to predict as K gets closer to N? You're going to predict the category that occurs most often in your data. So as K gets larger and larger, this K nearest neighbors classifier effectively becomes choose the most popular category and assign it to everyone. So we want to keep a balance between K not being too small, where it's inconsistent, and K potentially being too large, where we're just approaching the class frequencies.
If we run the tune grid on sort of an average example of a K-nearest neighbors, is it generally going to have that shape where it's kind of noisy and then there's a pretty clear optimized region and then it drops off?
Yep. So generally you'll see the pretty noisy region where K is small. You'll see kind of a peak in the accuracy, and then accuracy will drop off as K gets larger.
Do we need to be concerned about like false optimizing, like where it's giving us points that look optimal, but because of the way it's fitting the data, it's not actually optimal? It's like there's something there that we're not seeing.
Absolutely, yeah. So we might be in a situation where we have a sense of false optimality. We might be doing really well on the training set with small k. Are we going to do well on the testing data set? We'll find out.
So our accuracies are still like not that different.
Yeah, so our
So does it really
accuracies are
matter?
still pretty high. For argument's sake, let's increase this k. I don't want to increase it too much because it will take some time.
Okay, in 5 minutes.
Because right now they're still not changing by more than like 0.003.
Well, so the biggest K we could take would be the size of the training data, which is 513. Right now we're doing about 10% of the training data. Let's go up to 150. I may stop this if it takes too long. So the green bar indicates that things are still going. So we've added 100 more Ks to our grid.
So
Then we'll just hang out. Yeah.
When you're not, like you're not just testing for what all possible Ks might look like. Do you use Tune Grid and just give it like a data set with one value? If you just want to be like absolutely do 8 or whatever.
Yes, so if you want to force a particular choice, you can use Tune Grid with just one value. If you have multiple parameters, you will need to set all of them, but you can set values for all of those parameters. So it's done. That's good.
Yeah. It still doesn't get that low.
It really doesn't.
Still not that low.
The 2/3 though is your minimum, really.
2/3 is your minimum.
Lows 0.66.
So for a data set like this, when you're trying to distinguish benign versus malignant tumors, you'd really like to force it towards predicting it's a malignant tumor because that would force towards doing surgery. Is there a way to make the model do something like that?
So that's a good question. So the question is there a way to force or sort of bias the model in one direction? Intuitively, the answer should be yes. My guess would be that you would need to use some sort of a weighted distance and maybe give those malignant points more weight to implement this. It's not something that's going to exist in a package per se, but it is something that you could do if you were writing this algorithm out.
So there's nowhere that you can like lower the probability decision point or something. Like say if the probability is below a certain or above a certain point, you can. I guess that doesn't really work here because you're using distances. But
Well, one thing that you could do is actually extract predicted probabilities. So not only is train going to, when it predicts, you'll get those predicted classes, but you could also get those predicted probabilities. So if you wanted to accept a lower probability to classify in, say, malignant,
Yeah.
you could do that, and that would be one potential workaround as well.
So like if the malignancy probability of it being malignant was over, let's say 20% or 30% or something,
Mhm.
regardless of what the other class probability was, you're just gonna force classify this as possibly malignant. And then
Absolutely.
let a human figure it out.
You could do that. Yep. So I've set this to go up to k equals 500. We'll come back. We'll let that go for a little while. Next thing I want to do is think about visualizing these k nearest neighbors predictions. So here is cell size, cell shape. These are both related to uniformity. So these 1 through 10s are how uniform the cell size is, how uniform the cell shape is. So is it kind of a round cell? Is it all twisty-turny? If we have less uniform shapes, more likely to be malignant. Larger cells, more likely to be malignant. Here we're just looking at the full data because we've got that breast cancer too. Let's take a look at some predictions from this. So here is the k nearest neighbors boundary using optimal k Euclidean distance. Notice here I've used a 10 by 10 grid for prediction. That's because the original values could only go from 10 by 10. Within each of these, the points are jittered, so they're spread out very slightly. And then these plots have the testing data overlaid. So it looks like larger cells that are more irregular, we will predict to be malignant. Smaller cells that are more regular, we'll predict to be benign. Here, all of our other predictors are set to be at their mean value. So if we change those other predictors, now this is what it looks like when all of those other measures are at their minimum. We'll predict benign throughout. One thing you can do to sort of assess this performance is plot it against a couple different ones. So we have the mean plot here, all others at their 10th percentile, bless you, all others at their 25th, all others at their 50th. Something about the 75th percentile for all of the other variables, we're predicting a lot of malignant tumors. At the 90th percentile, we sort of go back to predicting more malignant tumors. Yeah.
So might this be what Molly's getting at, where you, like in this case, you would want to use the 75th percentile, because like when you showed the mean one, I was like, that's not good because you're predicting so many malignant tumors as benign. But is there a way to, there's some way to plug that into the model, not just like in a plot though?
So there's ways to plug this into the model. All of these variables are represented in the model, cell size, cell shape, and all of the others that we can't see. But just because we can visualize in 2D space, we have to make those other changes in the background. So here we're only looking at cell size versus cell shape. Now a clinician, not a statistician or data scientist, might have other variables that they would want to see prediction maps for. And again, that's where context really helps you make your decisions. Josh.
The book talks pretty heavily about normalizing the data to not allow certain predictors to take over. And it seems in this case it may be where you could scale the predictors that are most significant or the ones that are kind of common sense to help you get a model that predicts better. Because clearly here we can tell what's a good model look like and what's a good model not look like.
So that's a really important point too, and it's this idea of scaling your variables or pre-processing your variables in machine learning. Especially when you're calculating distances, the units matter. The distance measured in miles is going to be different than the distance measured in kilometers. If you just compare those numbers, it's not really going to be an accurate assessment. With this data set, we actually don't need to worry about that quite yet. It's because all of the input variables are already on a 1 to 10 scale. So this data set is sort of set up to look at k nearest neighbors really nicely. For other variables, we will want to process our data first. We will want to scale it first. Yeah?
This is my last question for my clinician. is there a way to look at what for the values that it's misclassifying, if it's doing like a type 1 or type 2 error, if you were to decide which of the categories would be each type?
Absolutely. Yes. So we could look at just a simple confusion matrix, for example. We could look at where we're misclassifying.
Makes sense.
Other questions? Okay. Let's see if our K up to 500 is done.
Maybe a little
Too many
overdone.
ties in canon.
Too many ties. So once we've gotten to the point where K is nearly N, we have a lot of ties because we're getting essentially all of the data.
Yeah.
But that's what happens to our accuracy.
Gotta find this floor.
So certainly somewhere, just based on this data, something around 20% of the observations in the training data, that's where we start to see a pretty dramatic drop in how well K nearest neighbors performs. That's not unique to this data. So you wouldn't want to try K any greater than that.
Why is the floor at 2/3?
So
Is
the
that
floor-
'cause There was,
Go ahead.
There was like 1/3 of the data was benign, 2/3 was okay.
Yeah, so the floor is at 2/3 because 2/3 of the data was malignant.
Okay.
So the floor is always going to be at the most popular category. Other questions?
It's a really janky way to.
Hmm?
So that'd be a really janky way to figure out what the proportions are in the data.
It is. You could certainly get the proportions in the data from doing this. There are easier ways, but you could do it.
Most impractical algorithm to calculate Cohen's gamma.
Yes.
I wrote a Python function one time to calculate the addition of two numbers using sleep statements.
I do kind of love those games where it's just how terrible can you make an algorithm? They're very funny.
They are interesting. All right, so let's talk about another possible way to evaluate classifier models. One metric that you'll see pop up sometimes is something called a receiver operator characteristic. So we'll plot a receiver operator characteristic or an ROC curve. This is a plot summarizing how well the classifier does on the training set. What this plot tries to get at is that relationship between type 1 and type 2 error, false positives, false negatives. So what will happen is we'll plot the false positive rate against the false negative rate, and we'll try to look for the relationship. The ideal curve is going to hug the top left corner, and we'll talk about what this looks like on the axes. Caret for some classifier models spits out an ROC area under the curve. The closest this is to 1, the better the performance of the classifier. In order to construct these, we do need to have the probabilities that are predicted for each class. We can do that using the predict function. We can actually do this for any classifier, not just K nearest neighbors, by adding an additional argument that says type equals prob for probability. So what gets returned is the probability of a benign tumor compared to the probability of a malignant tumor. Now, you can see that this K nearest neighbors algorithm looks like K is in most cases set to maybe 9, except for where we have ties. So where there are ties in the distance, we're drawing in more points to help make that decision. So that's why you see 5 9ths, 4 9ths, 1 9, 8 9ths, and then some non-9th decimals. So to calculate this ROC, we can look at a 2-class summary here. So I'm going to store my results in the following way to get this. So my results are the observations in the test class. So these are the actual observed values. Pred is the predict. The benign and malignant columns, these represent the probabilities. So here I'm taking the probability, column 1 from that probability prediction. That's what's giving me the benign. To get the malignant probabilities, I could take column 2 from those predictions, or I could do 1 minus the predictions from column 1. Both of those should work. And then I'll take a 2-class summary on the results. The levels are the values that we're looking for. So it's going to look for a column for benign, a column for malignant. Sensitivity and specificity. Do you guys remember what those represented?
True positive and true negative.
Yep, true positive, true negative. ROC then gives that area under the ROC curve. This is very close to 1, so we're predicting pretty well for this data.
Specificity is negative. Sensitivity is positive.
They're both positive.
I'm sorry.
No,
which one?
the true negative, true positive, which is true.
Oh, sensitivity, this is true positive. Specificity is true negative. Now, unfortunately, these ROC curves aren't included in Caret. We have other packages in R to use them. One that I found in Light has been the ROC-R package, so ROC in R. Again, we can use this on classifier models of any kind, so not just k-nearest neighbors. What it looks like is this. So this ROC curve is going to plot the false positive rate against the true positive rate. So what we want to see is this false positive rate shoot up pretty quickly in terms of true positive rate, and then a curve that looks like this. So we're allowing that false positive rate to change. It's changing pretty quickly because we're using different iterations of the model, and then the colorization is just fine. What is being reported with that ROC is the area under this. Again, last thing, sensitivity and specificity, since we glossed over these previously, just a reminder, sensitivity is the true positive rate, specificity is the true negative rate. So that false positive rate is actually 1 minus the specificity here. Again, the success and failure, so what is the positive, what is the negative, that's arbitrary. The success is usually taken to be the most frequent category. So for us, the success would be the malignant tumors because there are more of those than the benign tumors. So if we want to look at how we're doing with our classifications, we can make a confusion matrix. I didn't want to see the whole confusion matrix output, so I just made a quick 2x2 table of those results. So I took the results data, grouped it by predicted and observed, and then summarized. This is the testing data. There are only 3 tumors that are misclassified in the testing data. So we're doing pretty well with this algorithm. Another way to visualize this might be to make a plot of the predictions. So for the true benigns, we're predicting most of them to be benign. Here's the 2 that we mispredicted. For the true malignant, we're predicting most of those to be malignant. Here's the 1 that we predicted incorrectly. The new thing about this ggplot is the scales argument in the facet wrap. If you haven't seen that before, what that does is allow the x and y axis to change for each of the facets. All right, so selecting optimal K, we talked about this a little bit previously, so we'll go through this fairly quickly. What I want to highlight here is that depending on the metric that we use, this optimal K can actually change. So here's the optimal K going from K equals 5 to K equals 50, using that accuracy as my metric. So it looks like the best K is right here at 18. If we we allow kappa, so that improvement from chance, to be the best metric, we still get 18 as our optimal choice, but the pattern can change a little bit. So depending on which metric we use, we might have a different optimal K from one to the other. Anytime we're evaluating a model, we could consider, or we should consider, the effect of the metric, how our measure is actually related to the accuracy. If K is the same for both metrics, awesome. If K is not the same for both metrics, we might dig a little deeper. The other options that are built in here are something called RMSE and R squared. So for example, if I try to plot the result of this classification measure using RMSE, I get an error. Stat modeling graduates, what does RMSE represent again? Root mean square error. So it is the square root of the difference between the predicted and the actual value. When we're doing classification into categories, it's a metric that doesn't really make sense as a measurement. So it will only calculate for the sensical metrics, the ones that are sensical given the data. All right, so the last thing I want to show you today is how to do this with Minkowski distance. So how to generalize that distance measure. And I apologize that these slides or this code is not in your notes. The only thing that's going to change, though, is the method. Minkowski distance is method KKNN. So looking at the parameters, again, our K is taken to be 5, 7, and 9 by default. We have some tuning parameters here. There are some other parameters that are part of this model. So we'll have a distance parameter. That's actually the parameter of the Minkowski distance. So that is P. We can set that power that we're using in our distance metric. K max is the largest number of neighbors to be considered. There's a word that pops up again, though, when we look in the documentation of Minkowski distance. For each row of the test set, the k-nearest training set vectors, according to Minkowski distance, are found, and the classification is done via the maximum of summed kernel densities. So we saw this term previously. Naive Bayes was using a kernel density estimation technique as well. So what the heck is this kernel density? Oh no, shoot. Well, let me actually show you. Let's change this back down because I'm going to need to recompile the notes so you can actually see this kernel density stuff. Well, what?
I just Wikipedia'd it, and it reads like magic.
Kernel densities are kind of magical. We're going to spend a lot of time with them when we get to something called support vector machines, which are also kind of magical. But so that we're not fumbling our way through the forest, I do want to talk about what they represent very briefly. There's also another trick that I'd like to show you today because it will help make your life easier. All right, so let's see if we caught that up. We didn't. All right. Well, essentially, here's what a kernel density function is. So a kernel function is essentially a positive definite function on a distance or a difference between two variables. So I wonder why that's not breaking correctly. So any kernel density is just a function like this, where if we take a sum of some constant times this function, k represents the kernel function evaluated at our xi and xj. It's a function where this is guaranteed to be non-negative, guaranteed to be greater than or equal to 0. There are lots of different kernel density functions that you can use. Here's the big idea. These things measure similarity between two observations. So they tell you how similar and how different the observations are. So think of them as another way for now to measure distance.
Is this related to like distance between and distance within? When you're talking about groups?
Not quite. So distance between versus distance within, you can certainly use these kernel functions to measure them, but they're just other ways to account for distance. So different kernel functions that are used, there's a whole lot of them. We could do a linear kernel. We could do a polynomial kernel. All of these are written in vector notation. So again, we'll come back to this once we have a bit more matrix and vector review under our belt. Polynomial kernels look a lot like Minkowski distance. They are. Got normal or Gaussian kernels. This is not the Gaussian kernel. This is the Laplacian kernel. Suffice it to say, there's lots of different shapes of functions that we can use to calculate this distance. The ones that show up in Minkowski distance that are most often used are rectangular, that's right angle distance, something called optimal distance, and then Gaussian, which represents the Gaussian kernel distance measure. One thing that you may see happen when you're trying to modify tuning parameters is something like this. The tuning parameter grid should not have columns k max, distance, and so on. This is a known typo in Caret. It should have these columns. So anytime you see this error, these are columns that need to be present in your tuning grid, not absent in your tuning grid. Everyone makes typos.
How long until it is fixed?
It probably will not be fixed because Max has moved on to tidy models.
Darn.
It's kind of
It wouldn't be a hard fix.
yeah. It sounds
It's
like
not a hard
it
fix.
sounds like a pull request and GitHub isn't order.
I think there is a standing pull request.
Control H parameter grid
Yeah.
should not have replacement. Parameter grid should have.
Yeah. That's just something to keep in mind when you get this error. This is what you need.
I think it's a booby trap for not professionally trained.
No, it might be.
It's a booby trap for
This is
people who
as far
don't
as
know
they
how to
can
use
go.
Stack Overflow.
Yeah, for sure.
Honestly, that's fair.
We'll leave it at that.
Grandmas could say that about programming in general, though.
Yeah, if you can't use
All
Stack
of
Overflow, you're gonna
programming is a
anyway.
booby trap for Stack Overflow.
Yeah.
So let's say that I create a new tuning grid, and this is a lot like what Kelsey suggested, where I'm just forcing it to choose some values. I kept my grid relatively small at 48 to do this, so my maximum allowable K is 5 to 10. Distance, so this is the power term in my Minkowski distance. I let that go from 1 to 4. And then kernel, optimal, and regular, just to see what would happen. I'm using an expand.grid function here to expand all of these out. So this is all of the three-dimensional ordered pairs. By default, I don't get column names. So make sure that you are adding those using a call names. I did this. It took about 2.5 minutes. Not bad. So looking at the results here, it looks like Minkowski distance of 4 had the lowest, or Minkowski distance power 4 had the lowest accuracy. followed by 3, 2, 1. So simple distance measures looks like they do a lot better for this data set. Looking at the number of K neighbors, this optimal with K equals 10 had slightly higher accuracy. However, the gains over the rectangular or Euclidean distance, not that much. So the last thing that I want to talk about today is something completely unrelated to implementing any machine learning technique other than time it takes to execute. And that's something called caching. So caching refers to running code just once and saving the results for later. If you're working in R Markdown, which most of you are, you can do this really quickly in RStudio by in the declaration of your code chunk. So all the way over here, adding this statement, writing cache equals true. What that does is that the first time you execute this chunk of code, a separate R directory will be created with a separate R data file. So if I go to my machine learning folder and look at the class notes, I'm going to see for this section a cache folder. This cache folder contains the results of my chunk, the results of the code that I just ran, as an RDB file, RDX file, RData file. If we look at that, all right, fine, we won't. Why would iTunes be a good way to open this?
I think they have
To see it, like, shouldn't.
That's kind of like there's a built-in alias in Microsoft 10 where on certain machines, if you type Python in the command line, it will launch the Microsoft Store even if you have Python declared in your path.
irritating.
That is delightful.
Then you have to go turn the aliasing off to get it to actually run Python from the command line.
I've not seen it happen before, but it's very irritating.
So what is happening when you do this is that all of the results are being saved in these nebulous RDatas, RDXs, and RDBs. Every time I knit this code afterwards, as long as I don't make any changes to my code chunk, it's going to pull those previous results. So that means that if you have something that takes a while to run, oh, there they are. That's why I couldn't find the previous chunk. It was on my other monitor. These caches don't really mean much unless you know how to interpret them.
Yeah, that's just.
This is what one of them looks like.
Straight not
That's
convinced
what the
that
development-
encoded correctly.
I too can read Sanskrit.
But R does know how to read that back end and re-access the previous results. So if you're working in R Markdown and want to save yourself some time, caching can be your best friend. Jupyter, I believe, has something similar, but I don't know the exact option.
Write it out as a CSV.
I've been
Call it
a fool
later.
this whole time.
I have effectively done that for in Spider though.
I needed to know that like 2 years ago. This is life changing.
I believe you can cache Python results from within RStudio.
That would be interesting.
We are about out of time. We'll stop here. Next week, since we've talked about a lot of classification methods sort of separate from one another, I want to spend some time doing some case studies. So we'll do some labs next week where we'll compare different classification methods. We'll actually have you guys do some of the comparison and report back. Look for an email if you need to bring your laptop. You will at least one day next week, and where we meet. When we do labs, we may meet in the conference room instead because it's got some fun technology for sharing results. Have a good weekend, and I will see you guys on Tuesday.
So